Now let's do a review, and also, while we're in the midst of doing a review on the whole energy stable and energy landscape business, we're also going to start talking about radicals and what are radicals and how do they work. Now, if you go back to the last lecture, the first part of this lecture, you'll see that I did a radical mechanism, right? And that mechanism is true enough, but it's a bit more involved than I originally had discussed. And radicals are quite fascinating, and they're an important part of um, chemistry. So it's worth revisiting that in greater detail, and it's worth revisiting it in the context of what happens energetically after the chlorine-chlorine bond is broken. But let's start from the top. So in the radical reaction above that we originally started out with, we had some sort of interaction that started with methane. And there was chlorine gas. And we are going to use light. As it turns out, chlorine gas and light, when they come together, light breaks up chlorine gas into chlorine radicals. So if we wanted to really go back over where we started, how does this reaction go? So we know this reaction, for instance, just doesn't happen in the dark. So that there is some sort of something to do with light. Essentially, light behaves as a catalyst. All right. So if we know that light initiates the reaction, and we know that chlorine is sensitive to light, and we know methane is not, you've never heard of anybody say, no, keep the gasoline out of the light, it'll turn into something else. It doesn't. Gasoline is not sensitive to light. Chlorine is sensitive to light. So we know that something happens. And the only way, as I'd previously said, for chlorine to actually start working under light is you have essentially radical formation. This bond splits, and you get two chlorine radicals. All right? And what is that? If we draw the full Lewis structure of a chlorine radical, you got lone pairs all over chlorine and then one dot. All right? Chlorine radical. This is a reactive species. It is not full octet. So what happens now in this reaction? All right. So in this reaction, when it's going to go and it's going to react with our methane, all right, chlorine radical, unlike chlorine gas, that is a reactive substrate, right? So now, I'd have gone to great lengths to tell you that you can't really pull these protons off. Methane is not acidic. But a chlorine radical is just like, I don't even care how not acidic you are. You're coming with me, all right? And so, it's going to go and just grab it. And it's going to take one of those electrons. It's going to kick one electron back off to the carbon. And it's going to go and form a 2-electron bond with chlorine gas, or chlorine to make HCl. So what does this then generate? That makes chlorine now has a 1 electron from the original chlorine, 1 electron from the methane, right? So if I were actually, let's just go into donk. Keep that clear. So 1 electron came from that original bond and 1 electron came from the chlorine gas. So now chlorine has a full octet. What happened to this one though, right? Now what's happened here? Let's go back over here and take a look. Well, the carbon now has some sort of radical on it. So we've got a radical center, and it's a radical, so it's got 1 electron in an orbital. And in order to accommodate that, you're going to rehybridize. It's going to rehybridize itself into an Sp2 configuration. And so you end up with something that looks like that. Now that has a radical. Carbon radicals are incredibly, incredibly reactive. And somewhere there is a another chlorine radical, right? Because that's 1, so that kind of went down here to 1. But there's another one. There's still another chlorine radical over here. All right? And that chlorine radical can come in, and that radical can combine. And what we end up now is our final product. And that is formed with an electron from the carbon and the original electron for the chlorine. So that's that bond right there, okay? Another thing that can happen is this. So once you have these, we can go back now and look at the actual components of this chemical reaction, right? We can see that there is a reaction system where you have so then what can happen here is actually this carbon radical is just incredibly reactive. And it can actually propagate this reaction. You can form a bond. So this can actually abstract a electron from there and recombine, right? And this is actually 2 electrons in this bond. So that will make a new chlorine radical. And what you'll end up with is something now that your final product will be carbon H. And then you'll have that electron from the carbon, and then you'll have the electron from the chlorine, and that'll generate 1 bond. You also still have that additional chlorine radical, all right? And this chlorine radical, you know, you could have, that chlorine radical can also do some chemistry, and that can go off and do this entire thing again, right? So then you generate a new chlorine radical, and it goes on and it goes on and on and on. You don't actually need light to continuously source it. You end up going essentially forever. So once you start the reaction with light, essentially you have the reactive intermediates are going to be this essentially this chlorine radical. It's going to be flopping around everywhere. And this carbon radical, those are actually reactive intermediates. You can observe them, you can isolate them, you probably can't handle them. I mean, you probably wouldn't put them in your hands. That probably might burn a lot. But they are genuinely reactive intermediates. And so you can now draw a good potential energy diagram for this entire process. Okay? So you can start off with your reactive intermediates. Your chlorine radical that you created from light is going to come and react with your methane gas. All right? And then that is going to have a transition state. And that transition state is this high-browed thing where you have arrows going everywhere, and you can't isolate arrows, and it's sort of a hypothetical looking thingy anyway, but it kind of looks like this, where you have the chlorine is abstracting, a bond is forming between the chlorine and the hydrogen, and the hydrogen and the CH3, that's breaking. So there's a breakage point, and then that forms an HCl, right? So that's obviously a stable molecule. You can isolate HCl, that's a gas. You can dissolve it in water to make hydrochloric acid. And then you make a reactive radical, right? That is a reactive radical. It has a finite lifetime. You can observe it. It is extremely reactive, so it's quite short-lived. And then, as I've illustrated here, it can undergo sort of this bond scission crazy arrow pushy thingy with this, where you see that we have a bond that's going to form. So a bond starts forming while a bond starts breaking. And that is another transition state in this whole process, where you have H3C, and then they are getting to start to form a bond between Cl, and you're breaking a bond between Cl, and that's your transition state on your way to your final product, which is, again, a chlorine radical and your methyl chloride, or chloromethane. And that summarizes essentially what you've learned. We'll put labels on these: starting material, transition state, also a transition state. And then these are your intermediates. And this pit right here, this well, that's where you're going to find your intermediates. This coordinate is your potential energy. And this is all being mapped over your reaction coordinate. All right. And the minimum amount of energy necessary to get this reaction rolling in the first place is your activation energy, right? And you can measure your activation energy from here. That's your energy of activation. You do have, but presumably if you can get over this hill, you can get over that hill. All right. So this is what's called the rate determining step, and your rate constant. This is the minimum amount of energy you need to get anywhere, is the tallest transition peak. So that is your activation energy. Remember, your activation energy is the tallest peak. That's important. This difference right here, all right, that is your Gibbs free energy, the distance between the product and the starting material, all right? And your Gibbs free energy, that kind of tells you how reversible this process is. You can ask yourself, can this chlorine radical go and re-abstract the chlorine to get back to this? You bet it can. You bet this whole thing is reversible. And that can go backwards. So, and the amount of the relative ratio, when you're done with this reaction, you say, I'm done, all done, okay? At time infinity, you will have some ratio of chlorine radical and chloromethane, and chlorine radical and methane. And that is directly proportional to delta G, Gibbs free energy, because delta G is directly proportional to equilibrium. And the EA, that directly relates to the amount of time it's going to take. So I've drawn this to show that there is some amount of time necessary to get there. There are a couple of things that I wanted to point out, because radicals and radical chemistry are important in the context of organic chemistry. And this is just an example with the initial reaction occurring with chloride, and chloride radical being particularly ferocious. It's really, really strongly reactive. Fluoride reacts faster, so basically anything that wants electrons, the more electronegative your system is, the more reactive its radical will be. And so fluoride would be a more reactive radical than iodide. What exactly are radicals? So let's press onward and let's kind of explore the radical that I drew. And you know, now I drew this Sp2 hybridized system, and the Sp2 hybridized system kind of makes sense geometrically because you still have this. You have this lone pair, this open pair. It is an electron deficient system. It's Sp2 hybridized, and you know, how is this thing just not going? How is this thing just not going nuts, right? How can you have an open, empty orbital? Uh, and that can actually be explained through how radicals are stabilized. So, methyl radical is not a very stable radical. There's really nothing there that particularly helps promote its stabilization. But let's say you wanted to make a stable radical. How do you do that? Well, by definition, this radical is electron deficient. Literally, it doesn't have a full octet. It's missing an electron. It's electron deficient. So if you wanted to stabilize a radical, I suppose you could just employ the inductive effect. And the inductive effect, the same way we induce dipoles, if we have something that can donate electrons into that orbital, that will stabilize it. And so it turns out that if we just replace that H right here with a CH3, we will stabilize that radical. That radical will actually become much more stable. All right? And this is really where the geometry starts to make a difference. Let me clean that up just a bit because the inside got a little messy, I guess. You have that radical right there. You got an electron right there. Now, how does that work? In fact, the more substitutions you put on it, the more stable it becomes. And so we see that this stabilization actually, and this stabilization occurs through this geometry because of something called a hyperconjugation effect. So if I actually redraw this out, so now I have more actual three-dimensionality. Okay, orbitals, just wave functions, right? They actually can exchange electrons through space. So I've drawn this out, so now it's got three-dimensionality. Let's actually eliminate that and drive home the fact that this is a two-electron bond. Hyperconjugation through the inductive effect is actually because these electrons can kind of transmit their electroniness, their negative energy, their negative stabilization into that orbital, giving us an overall induction of an electron density moving that direction. So inductive effect is essentially pushing electron density into that orbital through some specific method called hyperconjugation. And hyperconjugation is superlit. This is hyperconjugation. Hyperconjugation very rarely happens for anything else other than integrating with some lone p orbital. If this were, say, a carbocation, then you could have hyperconjugation where the electron density goes in there. And we'll discuss carbocations in just a second. But you can imagine this stabilization through the inductive effect and through hyperconjugation would be even more if this were a CH3 and that were a CH. Then all of these could go in there. So as it turns out, when it comes to radicals, the more substituted, the better, right? So the inductive effect essentially comes down to the more substitution, the more stabilization. So a primary system like this one, right, that is more stabilizing than the methyl system, the no substituents. And a secondary, where this is CH3, that's more stabilizing. In a tertiary, where that one and that one CH3 and that one CH3, where they're all CH3s, that is going to be the most stabilizing. Okay? Another way to stabilize radicals, as you can imagine, just like you stabilized carbanions and carbocations, is through resonance. So in order to do resonance, of course, you need to have a pi system. So pi is here. And if you have a radical here, you can draw a resonance structure that looks like this, where now you have the radical on that carbon, and that goes here. And you can even draw the arrow pushing to get you there. Remember, you're drawing a hook arrow, one hook arrow, and then a hook arrow here. That throws your electron onto that side. All right, so again, with resonance, you have to have these p orbitals, and the p orbitals continue to help push these things around. And your radical is in a p orbital because radical's sp2 hybridized. So in this particular system, all the carbons are sp2 hybridized, and they're all in conjugation. Now, all these rules are basically the same for carbocations. Like radicals and carbocations are pretty intimately related in all of these regards. So this is all about radicals. And radicals the only difference is the radicals use these like little fish hooks, because the radicals you're always moving one electron around. Carbocations, likewise, are sp2 hybridized, right? Because if you have a empty p orbital here, right, that makes a lot more sense than having an sp3 hybridized orbital empty. What's it hybridized to? You know, it's not bound to anything, so it can't. If an empty orbital is going to be a p orbital, a half-filled orbital is going to be a p orbital. So in the case of, let's draw up here, in the case of carbocations, you have the same sort of deal as in the radical case. It's also sp2 hybridized. This is also electron deficient, I mean even more so, right? Because it's electron deficient in the sense that it actually only has 6 electrons in its orbital. And so the same things promote stability in a carbocation. If you want to promote stability, you do substitutions, because then you add CH, H, H, and then you have hyperconjugation right into that, right? And the more substitutions you add, the more stable that becomes, right? Because now you have hyperconjugation into this thing from all directions. The carbanion, on the other hand, right? The carbanion is different, okay? So the carbanion by itself is sp3 hybridized because it's filled. It's got a filled orbital, right? So you have a filled orbital and it's negatively charged. You know, it's got 2 electrons in it, but it is full. It has a full octet. So with a carbanion, you have the same sort of geometry as an sp3 hybridized system, okay? This is now an electron rich. It is a full formal negative charge. All right, so methyl carbon, a carbanion is going to be sp3 hybridized, right? Now, if it's in resonance, so I should mention specifically not in resonance. All right, now if it can resonate, if it can form a resonance structure, then it's a little happier, okay? Then it's sp2, and I'm going to talk about that in just 1 second. But carbanions actually, you can imagine now if you have substitution, this is CH3, and that's CH3. You know, you've got your hyperconjugation. Now this thing is like, go away, I've already got electrons. So actually, carbanion chemistry, substitution is bad. You don't want substitution. So in carbocations and in radicals, you wanted the more substitution you have, the more stable they are. And that is true for both radicals and carbocations, right? So I even write up here, substitution good for carbocations. Down here, substitution bad. Oh, all right. So you don't want substitution. More substitution, more unstable your carbanion, okay? Now, I mentioned resonance, okay? And in resonance is a good thing for carbanions. Unlike substitution, resonance helps distribute those nasty electrons over a larger group over a larger area. So now, instead of having all those awful electrons located on just one carbon, in this particular example, I can now spread the misery onto multiple carbons. I can draw this thing right here where we have some sort of negative charge. That actually is better. And in this particular instance, in this particular case, in order for there to be resonance, this has to be Sp2 hybridized, all right? So resonance makes your carbanion Sp2. But if it's just non-resonating, it's Sp3. So I'm going to write it down here. Carbanion is Sp2 when resonating. But it doesn't change any of the facts, all right? Resonance stabilizes it. So this is sort of the little nuance you want to keep in mind. Substitution here is good because that created resonance. Substitution up here that does not create resonance, bad, all right? So now we've covered 3 different reactive carbon intermediates, all right? We talked about the radical. All right, and radical gives us radical. All right, let's go ahead and label this. We're going to call this reactive intermediates. H. Okay, we got radicals, right? Okay, easy peasy. We got, I guess I should draw that in there. Carbocations. Carbocations got a lobe there. A lobe. Carbocation. We had carbanions. All right. That's a carbanion. And there's actually kind of another one, you know, a kind of a neat one called carbine. So how can you? We've got. It looks like we've got everything covered, right? We've got 1 electron on a carbon. We got no electrons on a carbon, and we got 2 electrons on a carbon. What is a carbine? And in a carbine, you can have something that looks, well, bizarre, right? You have a lone pair in an Sp2 hybridized orbital. Those are filled, and then a totally empty orbital. So this is called a carbine. All right, and that's bizarre, right? So I've got like 2 missing things. So it's right, it's missing like a connector here somehow. It's missing its a bond, and it's got 2 electrons, and yet it's got an empty orbital as well. What? But that's true. Carbines are actually neutral, right? Because that was technically like a negative charge, and that's a positive charge. So carbines are kind of funny. They're neutral. They have a vacant p orbital, and they have a lone pair of electrons in a sp2 orbital. All right, and so how does that happen, right? How do you end up with some crazy nonsense like that? And these happen actually using some solvents and combining a base. There's this really popular solvent called chloroform. I imagine you've heard of it. Hopefully you've never gone and sniffed it. But chloroform is pretty common. Bit nasty. Don't really want to get it all over yourself. Used to use it as an anesthetic. But if you throw a really strong base into chloroform, what's going to happen is this electron is going to deprotonate it, right? It's going to do acid-base chemistry. And then that's just going to go and try to make a carbanion, right? And so in that particular case, you end up with what you would think is a carbanion. And so you have something where you have a lone pair here, and then you have your chlorine. And you've got a chlorine here and a chlorine here. Except carbanions are furious. That's a pretty angry carbanion. Like, you've got lone pairs all over these chlorines. That's, you know, that will never do. Something's got to give. And what's peculiar is that the carbon's just like, peace, and it's going to kick off one of these chlorines. So what does that do? It's just like, all right, you take both of these electrons and leave. And that is how you ended up with a carbon that has an Sp2. I'm going to redraw this so that it matches my drawing up there, but it doesn't really matter. This will be here, and then now it's going to depart. You leave a empty, it's going to be an empty orbital, and then the chloride and then that chloride are here. All right, so that has created a carbene. And it's funny because a carbene actually now can do crazy things. It can both be kind of like a carbanion, and it can also be a carbocation, in the sense that these electrons, just like we had, I showed you the lone pairs of like nitrogen, those can attack things and deprotonate stuff. It can do that. Also, it's got an empty orbital, which means that it can be attacked by lone pairs here. So a carbene is kind of a crazy reactive intermediate. And it is what you would call both interested in nucleophiles, as in it wants to go find something with lots of electrons, but also it wants to avoid it. So it's got sort of a very uneasy relationship with everything. They're quite reactive and quite interesting. All right. So summarily, carbocations. Right. Carbocations. Let's try to pick a new color. And radicals. More substitution. Good. Right? Tertiary is better than secondary is better than primary. All right? Carbanions. Substitution. Bad. All right? The most stable carbanion is just CH3 minus. And then it gets worse from there. I mean, CH3 minus is bad. And then it just keeps getting worse. Carbocations, you want that super duper saturated system where you've got a C, and that's positively charged, and then that's a CH3, and then that's a CH3, and then that's a CH3. That's great. That's better. I mean, it's not perfect. No, the carbon is still not got a full octet, but that's the stabilizing sauce that it really was looking for. All right. So how in that way, so what does that mean in terms of like being able to be predictive, right? What are the consequences, I should say, of this stabilization in terms of reactivity? Well, let's go down and consider in terms of reactivity, right? So from our last energy diagram, if we say we started off with a system like this, and we then had a bromine radical. So remember from upstairs, by upstairs, I mean way up here, right? We had this chemical reaction, and you have to now pick. All right, now, because the next step is going to be abstracting a hydrogen, the bromine radical. Okay, so per our energy landscape, this bromine radical can go around and sample. It can go pick off one of these, it can go pick off one of those, it can go pick off one of those. Those are essentially our three options. And remember, it can pick one off and then it can go backwards. Things can shuffle around. The thing that's going to really determine our reactivity is trying to decide which of the intermediates it makes is more stable. All right? So it can make one of two different intermediates in this process. One intermediate is going to be it's going to be one where, and we're going to do it twice, where we have either a radical here, or we have a radical here, essentially, right? Because this is essentially symmetrical, right? I mean, if you really, okay, I'll if you want to be super complete. your other one is just the symmetry equivalent of one on the left. It's that one. Now, which one of these are the most stable intermediate, right? Because this first process is going to, if we draw our energy diagram, you have your starting material with your Br dot and then your propane. And then it's going to have, it's what amounts to two different choices, right? It's going to either form the most stable radical, which is going to be a radical that has a lot of substitution, so it's going to be this one, or it's going to be a radical that ends up on a primary carbon, the less substituted position. And because the less substituted position, if you had to choose, it's going to end up here. So this is your, your primary substitution, which are these two, primary substitution, or it's going to be your secondary substitution, all right, which is going to be this one. So even if it went all the way up here, it could get up here, and then it's like, oh, that's a lot of climb, and then it falls back down, and then goes over here, right? Because the next step in this reaction is going to be formation of your stabilized radical species, either your primary or secondary, and then the final product formation. And your final product formation is going to be either this, where you now have a Br coming off of here, or it's going to be this, where you now have a Br coming off of here. All right, so let me organize this a touch more. So if we have, this is sort of our options more or less over here. Let's bring this over here. All right, so what do we get? So if we go through this route, then our final product, let me just draw that in, so it's Br dot, goes through that process. If it goes through here, and then it goes through this process, essentially Br dot, right? This is a symmetrically equivalent molecule, trying to drive that home. So your final product really is not going to make a whole lot of difference. These two, this is going to be about as energetically stable as this. There's no real benefit necessarily to having a bromine in the middle, although you may have some sterics between bumping into the two of these and this only having to bump into that one. I would argue that what we'll call compound 1 and compound 2 are roughly the same energy, but we'll draw the final product. So your primary comes down to roughly here, all right? And your secondary, they both come down to roughly the same places. So one is just a little higher. If you go through your secondary intermediate, you're going to end up with just a touch little higher, I guess, and that's going to be compound 1. And then if you go through your secondary intermediate down here, it's going to be compound 2. Now you see the biggest difference in this whole process is actually not your product. All right, the energy difference between these two, you probably can barely even see them. There's a huge energy difference between these two, though. And so the selection process of which ones it's going to go through is it's going to go through the radical, because this is a reversible process. It can go up to 1, and you're like, that's probably not where most things are going to go. Just like people, it's going to go through the lower energy conformation, which means that the overall reaction process was entirely dictated by whichever one was the easiest or the hardest one to form, right? Which one was the easiest or the hardest one to form? The hardest one to form is a radical on the primary carbon. The easiest one to form was a radical on the secondary carbon. That means that your product is going to be predominantly determined based on this, and nothing to do with down here, all right? So selectivity in this overall process is essentially related to which one of these activation energy barriers is the greatest, all right? And that will tell you which one is going to predominate in the selection process, whether it ends up on the primary or it ends up in the secondary. I'm sorry, I did that backwards. Whether it ends up on the primary or it ends up on the secondary position, that has to do with this energy difference. All right. Now, the narrower this energy difference, the greater of a mixture you're going to have. So in chemistry, you often end up with impurities or side products. And that's because these reactions have a lot of choices. And granted, in this particular process, the predominant choice that these things are going to go through is going to be to end up with a stabilized radical on a secondary carbon as opposed to a less stabilized primary carbon. Okay? And so, but you're still going to have some jokers that get over here. And that's going to be, in principle, either your final product or a side product, depending on which one you go with. All right? And that is the conclusion of that lecture.